This is a short video on how to solve second order differential equations that will have complex roots. And again, when you're looking at this equation here, you don't necessarily know that it's going to have complex roots. I'll just show you that it will and what you'll do in that case. And this is an initial value problem where you've got some initial conditions. The value of your function at 0 should be 1, and the last equation says the value of the derivative at 0 should be 1 as well. So you're going to use those at the end. So the first thing you should do is just find the general solution, and then you'll use those two initial conditions to help you figure out what are those coefficients C1 and C2 that you get. So when you have your differential equation, first thing you'll make is the characteristic equation. So in that case, it's just lambda squared plus 4 lambda plus 5 equals 0. So you're just using the A, B, and C again that are given to you in the equation. So you need the quadratic formula to solve this quadratic equation because it doesn't factor nicely. And when you plug that stuff into the quadratic formula, at the very end you should get these two answers, minus 2 plus I and minus 2 minus I. Now all we need is one of these, so we're just going to play with minus 2 plus I, the first one. And this is similar to the kind of thing that we saw in the systems of equations with complex eigenvalues. So the next thing that you do after that is one complex solution is just if I use the first one. So x is equal to e to the minus 2 plus I times t. And now what we're going to do is we are going to try to manipulate that expression down there at the bottom. And so I'll split that up into two pieces. When I distribute the t through and I apply some exponent rules, that's the same thing as e to the minus 2t times e to the I times 1t. Now you don't have to write the 1 there. I just want to write the 1 there for emphasis on what's going to happen in the next step. What we're going to do is I've still got that exponential with the complex number in the exponent, the e to the it. We're going to use Euler's formula to rewrite that. So this is the same thing as e to the minus 2t times, and now Euler's formula tells me that this should be just cosine of 1t plus I sine of 1t. So this is why I wanted to highlight that that 1 is really there in front of the t. So if there is like I times 7t, then it should be 7t inside a cosine. It should be 7t inside a sine. So that's all the 1's trying to highlight. Now what you could do is you could distribute that e to the minus 2t through to both of those, and you get this complex solution, e to the minus 2t cosine of t plus I e to the minus 2t sine of t. So that's one complex answer. Now, what I've underlined there in blue are the real on the left and the imaginary pieces of this complex answer. And I purposefully did not underline the I. So when you're talking about the real and imaginary parts of a complex number, those are real numbers themselves. So don't worry about that I there. All I care about, again, is what I've underlined in blue. Now, going further, the real and imaginary pieces on their own to that, you could check if you want. Maybe just try and plug in e to the minus 2t times cosine of t into this differential equation up here and see what happens. And again, don't worry about the initial conditions. I pinky promise you that it'll be an answer. And similarly, if you plugged in e to the minus 2t times sine of t, the other blue underlined piece, that's another answer to the diffie-q. So what have you got? The real and imaginary pieces are two real solutions to the diffie-q. And at this point, you either understand or you accept that, well, if it's a second order equation, then as soon as I get two, linearly independent answers, those are enough to make the general solution. In other words, every solution is just some linear combination of those two. So therefore, the general solution is C1 times the first one, e to the minus 2t cosine of t, the first thing I underlined in blue, and the plus C2 times the second one, e to the minus 2t times sine of t. Some students think of this as essentially you just drop the I in the green equation above. If you want to think of it that way, that's fine too. So that's the general solution. The next thing that we'll do, since we're asked to solve this initial value problem, now we'll use the initial conditions that I'm given above in orange there. So how do I use those? So again, what does that tell you? The first one says when you plug in 0 for t, this equation for x should be equal to 1. So let's do that. And so what does that look like? That is this equation here. When you plug in 0 for t, you should get 1 for x. And so that is what I have done for you in the middle there. 1 is equal to c1 e to the 0 cosine of 0, blah, blah, blah. All that stuff works out to just 1 is equal to c1. That's a pretty nice equation. At worst, you're going to have some number is equal to something c1 plus something c2. Now we're going to use the other initial condition to try to get what c2 is. And so in that case then, this says x prime of 0 is equal to 1. I need an expression for x prime. So we need to take our blue equation, that's x, we need to figure out what x prime is. And the way that x is written right now, that could be kind of rough to differentiate. So maybe what we'll do is we'll take the blue equation and we'll just factor out e to the minus 2t from both the blue pieces. And if you do that, you should have your c1 cosine of t plus c2 sine of t left over. Now I just need to apply the product rule one time to find x prime. And when you do that, again, the minus 2 should come down from the exponential times what you have left in the second function, c1 cosine of 2t, blah, 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 plus the first function, e to the minus 2t, times the derivative of the stuff in parentheses, in which case you get minus c1 sine of t plus c2 cosine of t. Now, that is what we're going to plug 0 in for t and 1 in for x prime. That's what this initial condition says. So if you plug that stuff in, you get 1 is equal to minus 2 minus 2c1, plus c2. Now I've put stars next to, in general what's going to happen. What you end up getting, you'll make a system of two equations out of that. So that'll always give you a system in c1 and c2. This particular system just happens to be really nice that right off the bat you got c1 as 1. So what you could do at this point is you could take c1 as 1 and you could just plug it in for this here, and you should get that c2 has to be 3 in order to make those two numbers add up to 1. So at the very end of the day, you've got your constants now, and so just plug those into the general solution, into the blue. You just told me that c1 is really 1 and c2 is 3 if they're going to satisfy these two initial conditions as well. In other words, the one curve that satisfies the differential equation that also satisfies those two conditions, the one answer to that is this guy right here.